Hello, I'm Neelam Shukla from Indian Institute of Technology, Roorkee. Welcome you all on my poster, which is on C6 and C9 dispersion coefficient for associated alkaline earth atoms with their singly ionized ion. The motivation for this work comes from the fact that laser cold atoms and ion have many important applications, such as in ultra cold atom physics, quantum information, etc. Most of the ion atom experiments use alkaline earth atoms and their singly ionized ion because of their special atomic structures. Experimentally, there are various cold atomic ion atom combinations have been investigated, including these combinations, for example, calcium atoms and barium ions confined in a hybrid trap. But there is a lack of theoretical studies for these combinations. Therefore, we have calculated two dipole C6 dispersion coefficient among alkaline earth atoms and alkaline earth atoms with their singly ionized ions. In addition, we have also calculated C9 dispersion coefficient for interacting three alkaline earth atoms as well as two alkaline earth atoms with alkaline earth ions. The methodology involved in this work: any general long-range interaction potential between the three atomic species in their ground state is given by this equation, where C6 and C9 are the dispersion coefficient for two-body and three-body interaction respectively, in which we are interested. Since these dispersion coefficient can be written in terms of dynamic dipole polarizability. Now, the dynamic dipole polarizability for atom and ion in their ground state can be divided into two parts, that is the core contribution and the valence contribution. The core contribution can be calculated by using the random phase approximation, whereas the valence contribution can be calculated by using sum over states approach, in which F is the oscillator strength, E is the energy for the corresponding state, omega is the angular frequency of the field. Further, the oscillator strength can be calculated using reduced dipole matrix element, which we have evaluated by using all-order method for alkaline earth ions and multi-configuration Dirac approximation for alkaline earth atoms. As I have mentioned that these coefficients are not available for the considered system previously. Therefore, in order to ascertain the accuracy and the reliability of our calculation, we have also calculated these coefficients using well-known fitting formulae, such as for C6 we have used Slater-Kiger-Wood formula, and for C9 dispersion coefficient we have used the formula given by Mizuno and Kihara. Now I will explain the result calculated by us. In the first table, we have shown the oscillator strength of the leading transitions for the ions and atoms and compared it with the previously available result. For ion, we can see that there is a good agreement between the present and the previous result. Whereas for atom, one can see for the triplet P transition, there is a slight discrepancy between the result. As one can also see that for triplet P transition, the oscillator strength is very small, and at this scale, this much discrepancy can be neglected. In table 2 and 3, we have shown the static dipole polarizability and C6 dispersion coefficient for two homonuclear alkaline earth atoms in their ground state and compared with the previously available result. And both the tables showing the good agreement between the results. Now we have calculated the dispersion coefficient for two heteronuclear alkaline earth atom, and we have also calculated this coefficient by using the fitting formula as I have explained earlier in order to compare our result, and both the values showing the good agreement. In table 5, we have shown the C6 dispersion coefficient for alkaline earth and interacting with the alkaline earth atom and their value by using the fitting equation. Similarly, in table 6 and 7, we have shown the dispersion coefficient C9 for among the three alkaline earth atoms and between the two alkaline earth atom and alkaline earth ions, and their values obtained from fitting equations. In the end, I would like to acknowledge these funding agencies. Also, these are the references. Thank you.